The simplest of which is to talk about, for example, how, let's just use temperature, and let's just use viscosity. Let's say the zero rate viscosity, so-called zero shear viscosity. Then you will find that this viscosity will diverge. This part, it's a smooth curve, usually. It will diverge around some point, and that is conveniently, let's talk about the first topic, is where where the liquid start to freeze up. They find no ability to move. So this, you have to cool this to minus 100 C to reach that point. What we are concerned for the 100 billion pounds, several hundred billion pounds of polymer being processed is the zeroth order is, of course, viscosity. So you can see that by changing temperature, how viscosity is changing very dramatically. This can be easily 10 order of magnitude. Much more. In fact, it diverges. 10 orders, okay? That's 1 with 10 zeros. So it's very useful to know how this red line looks like. Okay? So that's what we're going to talk about today. And this part is in the book. So this is not something you will get lost because it's in the book. There are other parts that are not in the book. I have to be just sure that I'm self-contained. So this is all in so-called the chapter 2 in 2.4. Which was just a very brief summary of this idea of time temperature superposition. Obviously, finally, we're starting to talk about the effect of temperature. Very important in polymer science because of this red curve. There's a little more than that. So, okay, we are on part 2. We're on the first part, not crystalline, but only disordered, amorphous. Let's, for example, pretend to, well, there are things you know, there are things you don't know. The things that you have seen it once is if you do a small amplitude oscillatory shear, you tend to find this curve. This being small amplitude oscillatory shear, small amplitude oscillatory shear, very often abbreviated as SOUS. This is something that I have once indicated to you, but basically it's the elastic part of the response of your oscillatory shear, and you have several regions. Remember we call this plateau wave last time. And typically it's given by e to the 3.4 power between these 2 points. Because this 2 point is typically just tau d over tau e. So we talked about this is the fluid part. This is the elastic part. Just depending on how you probe your sample. And this point, as you roughly know, is 1 over tau d. In other words, this is the point where omega of tau d is 1. So obviously, when you go to higher frequency than 1 over tau d, your polymer chain cannot replicate out of the tube. So they start, given the time you're giving the polymer, they stuck in the tube as you do this. So it's in that sense, it's equivalent to a cross-link sample. And that's why you see that red G prime levels off. In other words, stays as if it's a rubber band, a cross-link sample. So I just want you to make sure you're familiar with it. We make connections when we talk about salts in the beginning. And this is the region where this product is less than 1. And this is the region beyond this point, product larger than 1. So very much we only concentrated on this part without talking about this takeoff. This takeoff often is known as rubber to glass transition. In other words, if you like, remember, G prime is nothing but an indication of how stiff your polymer is. And you find your polymer getting stiffer yet as I increase in the frequency. Because when that happens, not only the chain cannot swim out of the tube, even at segmental level, the chain looks frozen. In other words, you are so fast, even the segment is not able to move within the frequency, within the time provided by the frequency, which is 1 over the frequency. So that's where it becomes rigid, more rigid, stiffer. You will see the concept of, or the role of temperature very soon. This is all at a fixed temperature. Ideally, that you see this. But I actually cheated when I say it's at a fixed temperature. It turns out, rarely you will be able to obtain this entire red curve with 1 temperature. And that's the power of time-temperature superposition. We will spend all the time we need to go through. So the right way to say is, this is, if you perceive you can sit at 1 temperature, what we call it reference temperature. Then this is the red curve you will see. And we'll soon, I will, in fact, I should eagerly show you right away why this is not possible to do with 1 temperature. So for example, your plateau width, which I kind of emphasized, let's say your plateau width already involves 6 decades. When I say that, I hope you know what I mean. I mean, the frequency on this side divided by the frequency on this side is 10 to the 6th. Okay? If you don't like 10 to the 8th, a huge number. And I tell you why this is physically almost impossible to do at a single temperature to obtain this information. What we know is your familiar parallel plate. That you can move one of your plate torsionally back and forth, back and forth. Okay? Because of many issues, including compliance issues and inertia issues, it cannot oscillate very fast. So the upper limit of this in all commercial instruments is 100. In the unit of course, people like to use so-called radius per second. Basically, in the unit of 2 pi t. So t is only 100 divided by 2 pi. Okay, that's what? That's about 16. Did I just do it wrong? Of course I did. Flipping is by definition, 2 pi. Or did I lose my... Christ. What happens here? It's crazy. 2 pi over 100. So the 6 over 100. That's the second. So to complete one cycle, it's 6 over 100 seconds. That's as fast as you can oscillate. Okay, translate to omega, we say that omega is 100. Your motor can be as slow as possible. There is a limit. But usually, your limit of your patience may come in. In other words, your omega is upper bounded by 100, lower bounded by the motor limit. Let's say your motor is good, 10 to the minus 5. Okay? Now, if it's 10 to the minus 5, your tau is 6 pi times 10 to the 5. Right? Because your t is always just 2 pi over omega. How long that is? 6 10 to the 5. How long is that? Isn't that approaching 10 days? I have the memory that 1 day is about 10 to the 5 seconds. So it's a week. Okay? And if you are having your dearly made sample and you have to do this at some high temperature, you may cook up the thing degraded long before. Many things can happen. But essentially quite infeasible to do to the 10 to the minus 5. But I'm only talking about, right? I'm only talking about the plateau. What about the other two sides that goes up, that goes down? So you can see it's mechanically not possible to acquire such a curve. So that's where temperature superposition comes in. We will speak about very slowly, gently. So we can switch gears and recognizing that there is a limit of your range. This symbol just means that it varies in this range. There's a limit of how much. We can do something, of course, comfortably. Let's say you can take a omega, very typically. Take omega equals 1. And then what you want to do in your lovely instrument is suppose you can change your temperature. And here, very briefly, just a piece of information. We're going to do our sample, hopefully. In fact, depending on which part. You may use both your cells, which is a parallel plate like this. You may also have, when it's in the solid state, you may also have what's called dynamic mechanical analyzer, EMA, where you do it in a tensor form. So you have it under pre-tension. okay? And then within that pretension, you do a little back and forth. So that basically the rest, so there are two options. This is for the solid state part. This is more for the liquid state part. You may have both instruments to get this full curve. But we are just talking about abstractly, then it's easy for me to just abstractly tell you what will happen. What I'm going to measure is, again, because it's oscillatory, I'm going to measure so-called G prime or E prime. G stands for shear, E stands for extension, which is this part. So imagine you could do it. Then you can see this part that's liquid. Let's just be fair. So we can say, oh, maybe my TG is here. Here? Which means above TG, it's liquid-like. And you may or may not be able to hold your sample. Meaning if I heat it up enough, it becomes honey-like, it will drip. Right? It will sag. This DMA won't work. So you have to, if your technician says, oh, I cannot do it, then you have to tell him, hey, you forgot for that region we use the parallel plate. Right? With parallel plate, you supply that information, you find it's very liquid-like, depending on the frequency. And then if there's entanglement, you tend to do this. And then do that. I know you have to get used to it, looking at it. Basically, I'm just looking at one frequency and try to probe the stiffness of your polymer. It will flow, and then at some point, this is simply a point where omega times tau is start to be as large as 1, such that as you cool down further, your tau d is large. And that's the same as this region in the plateau, right? The same as this region. Okay? So you have to flip your mind a little bit here. That changing temperature is equivalent to changing frequency. Why? Because only omega times tau is what matters. In other words, when you change temperature, you are changing your internal clock. Well, your internal clock matters only when you compare with your external probe, which is omega. So it's always only this product that dictates what you see. So as you lower the temperature, that's equivalent to increasing tau, then you hit a plateau. And if you cool further, that's like your tau d further increases, which is the same as in the other plot, that frequency increases, right? So it's the same feature. This feature of taking off is the same feature as this taking off as I cool toward TG. I probably did not plot well enough. Probably I should indicate my TG is my TG is here instead. Basically, there is a point. Okay, so that's one thing. The second thing I want you to pay attention to is the second thing I want you to pay attention to is to realize that, as we typically said, this is the same plateau modulus. And we have already went through this. This typically has a range between 0.2 to 2 megapascals. because of the way the packing length changes as from one polymer to another. The smaller packing length has a bigger G, such as polyethylene. The lowest G is that of polystyrene that has a big P. If you hydrolyze polystyrene, this P gets even bigger. Okay, so in your mind, this rubbery plateau is essentially on the order of 1,000. I just want to be sure. 1 unit, basically 1 million, megapascal. And you should learn that in glassy state, essentially it jumps another 3 order of magnitude. 1 gigapascal is basically what it goes to. Okay, this is rule of thumb. This is for all of your dear polymers. No solvent, right? This is all solvent-free polymer. So, any questions? Yes, please. Oh, good point. Meaning basically, it's not a very sharp transition. So it increases. I hope your question is not why it's, I think it's perhaps more difficult for me to answer if you ask why the modulus stops increasing when it's deeply glassy. Well, everything is frozen already, so it turns out nothing can further change. If you ask this region, right? We once said already in the last page, we call the rubbery glass transition region. And it's rather broad, this transition. It doesn't take place at a sharp point of temperature. It occurs over a range. Is that your question? Decreasing as you cool. So there's a second gear switching here, because previous page I was talking about viscosity diverging, right? So separately, the stiffness is also increasing, but not divergent. It increases to a level of 1 gigapascal. Other questions? Yeah. Good point. So entanglement, I was trying to give you a sense that this is, that you can perceive around this temperature perhaps is the reptation time matches the frequency, which it was 1 I used. So I may claim that, hear me now, anywhere above TG, your reptation time changes with temperature, right? By definition. Well, by definition. This is what we're going to talk about today. It turns out our polymer is rather sensitive to temperature in terms of its sluggishness, how fast, how slow. So the tau is changing all over the place. Clearly, if I use frequency of 1, I almost can indicate that it is at this particular temperature, my tau also reaches 1 second. Higher than that temperature, do I have reptation? Of course I do. I will have a time shorter than tau. Above that temperature, of course I also do. I will have reptation time much slower than tau, other than 1 second. So for that reason, There's nothing magic in terms of tau of reaching 1 second. The magic of this being important dictates what omega you choose, right? If you choose a different omega, this position will change to a different temperature. So it's in that sense, this point has no physical significance in terms of temperature. I know I said it rather convolutedly, but hey, this is a graduate course, meaning I'm teasing you. This is how much you have to work. So in any case, the behavior of your dynamic modulus is a function of this product, as I write here. Period. You can change this product by changing omega. You can change this product by changing tau, which in our dear polymers is by changing temperature. So keep in mind, our tau we discussed for the first time can be a strong function of temperature. So this actually is exactly where I want to be to introduce time-temperature superposition. There are many ways to do it. Let me do it this way, to be a heuristic, pedagogical. Remember, coming out of the cave, let's say this is what happens. In other words, my viscosity diverges as the right curve shows. We also know, we had so much experience by now, that our viscosity, aside from a modulus, is related to our internal clock. And you may even recall how much the plateau modulus changes with temperature. Well, it is rho, gas constant, divided by times temperature, divided by molecular weight, or if it's entangled molecular weight. And you can notice that there is a tiny bit of temperature dependence. It's linear in T. And don't forget your rho, which is density of your polymer, also slightly changes with T. Quite small, I think. So there is a linear dependence on T. But this is a absolute temperature, okay? So let's say if your absolute temperature changes from 300 to 400 Kelvin, how much is that? 25% change. Or 30, depending on which point of view. 30% change. So it's not much. Look, didn't I declare that this could be 10 order magnitude? Or even more? So it obviously nearly all of your temperature dependence comes from tau, not from G. Yeah, that part is clear, right? Right away. So your tau can change dramatically. And therefore, you can overcome the fact that your omega, let's say, I know upper limit you're going to use 100. Lower limit, very often, our patients tells us we don't go beyond 10 to the 2 or 3. I would even advise people not to go beyond 3. Because 3 is an hour. It's about 2 hours. Because 3 give you a T of 2 pi times 1,000. That's 6,000. That's a little over an hour. Nearly 2 hours. Properly bearable. And the stupid machine, I don't offend anyone when I say this, usually take several cycles before they make the measurement. When I say stupid, I mean, if you have a sine wave like this, perhaps you can just use a part of the shape to already indicate what the measurement is. But for accuracy, they tend not to do this and extrapolate the rest. See? Instead of using a whole cycle, you will use, let's say, a quarter of a cycle should be enough. But instead, in commercial instrument, as far as I know, usually take several cycles. So instead of 6,000 seconds, it could be multiple of that, let's say 3 or 4 of that. Wow. Pretty soon it's several hours. So, be my guest. This part, of course, is related to what your material is, whether your material tend to degrade over that time, whether you have time to, whether your instrument performs well at the lower frequencies, many things. So, conservatively, I would even give you, say, only under 2. Okay, that means mechanically, you only have 4 order magnitude. Okay? So you will only be, for example, since I'm fixed, I'm only willing to ask my machine to oscillate from. Here's what we do to get this curve on the lower right corner. That's a G prime over omega curve. You do this. You load your machine onto the parallel plate, and for many reasons, I will advise my student to do the following. So basically, you load the machine, you choose an amplitude. Just writing it properly. You choose an amplitude. Oh Lord. Which is typically small, so you don't agitate the sample very much. You don't go to wall slip limit. You just heard last time. Wall slip doesn't occur at a small amplitude, okay? Because you have to disentangle. That requires a lot of strength. So you oscillate. So the machine does this. You basically ask the machine to choose, when you sit there, you have frequency already. You ask the machine, I will advise you to ask the machine to start with high frequency. So start with 100. So machine quickly do, my hands are not fast enough. Basically 100 seconds. 2 pi over 100. So it's a fraction of a second. And it will do it until they can measure the signal. As I said, it takes several cycles. And then once they get the numbers, which is G prime, G double prime, because you measuring gamma, you're imposing gamma, you're measuring, go back to the original notes, you're measuring the so-called the torque or stress and how it shifted away from sine omega t with the delta there. It's all in the software, the machine basically the machine is trying to compare, of course, that your imposed signal like this, and then you stress, oh Lord, and your stress is offset. So if you have your, I know it's a lot of patience to write it well. So basically, you have your strand there like that. The machine will measure the stress, and they find it's shifted away. So you can even graphically imagine that if you shift the frequency around, you will be able to match that one. So you'll find the delta exactly that way, graphically. I know I'm not drawing well, but basically there are signs that shifted away from sine. It's the same sign, right? Sine wave, which is time, so you basically, you can shift them and you can exactly find what is delta from that. And from that, you can get G prime, G double prime. So, suppose you do that and you went through from 100. So then you move to the next frequency, and how frequent you want to choose between them, it's up to you. You could choose 10 points per decade. You have 4 decades, that means 40 points. The machine is all smart enough to do that. So at the end of the day, let's say you end up having that 4 decades being this much. Okay? Hypothetically. What do you do? What do you do to get the next 4 decades, for example? The next, you follow me, right? I did my experiment already. This is 4 decades. I get this much of the information, right? I'm asking, how do I find the additional information? We have to change temperature, right? In order to change tau, because omega times tau is what matters. Which way do I go to get the next 4 decades? Lower temperature or higher temperature? Absolutely, because lower temperature give you a bigger tau, and therefore, oh Lord, a bigger tau, and therefore this product will be bigger. According to this curve, that's where it is. It's going to happen at a higher omega times tau. So you patiently dial up your machine, go to another temperature higher. And again, you can only run 4 decades and collect that 4 decades. And then, if I want to, just to confuse you a little more, now I want to make sure I cover this part. The lower part. Now I want to cover a little more up here. Well, you do the opposite. Because this happens at a smaller omega times tau, which means I need to make my tau smaller, which means I increase my temperature. According to this curve, as I increase my temperature, my tau will come down. So that's the whole spirit. And you patiently run this for many temperatures. You have a question? Yeah. This is for anything. No, here's the most crucial point that your technician should not confuse you, or you should not make sure your technician does it right. Remember, we are focusing on just the glossy polymers. There you have all the possibilities to do all the ranges you have. If you have crystallization, and you just told me that you did this one, and you said to do the next one, you need to go lower temperature, right, to get the next decade. And you go there, boom, it crystallizes. Can you still do it there? Not really. Not really. So your TC, crystallization temperature, truncates your ability to do unbended superposition. This is all you can do is you go prior to when it crystallizes. Because your intent was to interrogate your molten state, your melt state, in absence of any other structures. Crystallization was completely, crystallization, I don't have time to expand on that issue. For many people in the literature, has the effect of gelation. Upon crystallization, it's like the samples start to gel because the crystalline part act. Did I hear this word before? Act like a crosslink. Not before. So that's why it has all the features of a gelation when you hit crystallization. And that's completely different animal. It's not what you want to characterize in terms of learning what is your repetition time or what is your relaxation time per se. Any other questions? So I'm just giving you the concept of this deeply useful idea of what we call it a time temperature superposition. So let me write down formally. So it's a time temperature. Perhaps superposition doesn't jump to you very straightforwardly in the sense that you didn't realize that what I just went through is going through a superposition in the following sense. What you typically do, I know it's recorded, so it's easy for you to go back to your cleaner notes. But what typically happens is once you finish this decade of measurement, your next decade doesn't do just that. I mean, I do it in order not to confuse you, but if you are confused, if you are confused, it's the time. So when I do the next one, I don't do it here. Like that. Sorry, I don't do it like that. I do it like that. Let me explain what I mean. Well, I do it like that so that there is this region that the two set of data will overlap. I need that set to confirm that they match as well in a region they both share. So it's this sense they are superimposing onto each other and keep going. So your next temperature choice will be important. If you choose someone too big, it's one way over there. Of course, it will not overlap with the one. So that's okay. If you don't know this temperature dependence very well, that's okay. You just come back to an intermediate temperature to fill up. Basically, you're eventually going to fill it up, depending on experience and whatever. So it may take many temperatures for you to do that. Okay. That's superposition in that sense. We can speak about a very essential, I see my thing shifted, this so-called reference temperature. So what do I mean when I say I present this whole, what we call master curve? It involves many measurement over many different temperatures. What do I mean by a reference temperature? What I mean is the following then. It means the temperature, let me just say it's this. It means the temperature where I imposed my mechanical measurement, where I actually did my mechanical measurement. In other words, at this temperature, when I perform my mechanical window, it happens to give me the data here. You get my point? Then the rest of the things are done at different temperatures. For example, the ones at the lower frequency obviously was done at higher temperature. The data above it obviously was done at the lower temperature. So when you see a curve like this, that obviously will tell you this is 10 to the minus 6. This is 10 to the plus 8. That's 14 order magnitude. Okay? Okay? And they report a temperature, let's say it's polystyrene. So they report a temperature of 140. Okay? Okay? Then you almost know what part was the data done at 140. It's done, you just look for where this range is. Right? So going through this is very helpful for you to understand where it comes from. But the reality is much simpler. You got the commercial instrument. Everything was automated. You just change temperature. After a few temperature change, the software just automatically spits out this whole curve, master curve for you. But it's a black box if you don't know really where it comes from. Now you see how it comes from. That's the key. So that's superposition. In the literature, it is also quite frequently recognized that there is a time-temperature equivalence. In other words, temperature is a way for you to change time, and time is affected by time. So they are equivalent. This represents time. This represents temperature. They are equivalent in the sense it is the product of the two that determines what you observe. So in the literature, sometimes they call this whole principle time-temperature equivalence. Yeah? Yeah. Of course not, just one of them. Exactly. No, of course not. It can be, it can be anywhere. But that was why I said it. But if you look for this range, between -2 to 100, or at least the cut of 100, that's clearly where the maximum you can do. So, right? Yeah, so that region could be, where that region falls, depending on what reference temperature you choose to represent this whole curve. Yeah, makes sense? Makes sense, right? And it's entirely arbitrary for your convenience, perhaps. And typically, you probably want to choose one, you want to choose the temperature that you will often wish to deal with, right? Let's say my processing is done at 140, then obviously I want to present this whole curve at 140 to see what, how I perceive my reputation to be, right? How I perceive everything to be. Indeed, this is otherwise completely arbitrary. But just to drive home this message a little bit more clear. So if I choose a lower reference temperature, where would this region go? Where this two vertical bar would go, right? Where would I shift? To the right or to the left? Yeah, so it would involve a higher product of omega times tau because tau is bigger now, because I use a lower temperature as well. So that's it. So it could be in that transition region, that bar. So entirely depend on, it's a good question, right? They entirely depend on what reference temperature you happen to choose. Okay. with all that hard work, but it's conceptually very simple, right? Very, very clear, very simple. With all that hard work, very simple. When I say that, I also mean I do want you to connect all the theory from dilute Zim theory to the Rouse for unentangled melt to the reptation idea tube model for entangled systems. They all found G prime, and of course also G double prime, to be a function only of omega times tau. Well, I should apologize for you. Not really. Omega times, if you're going to call Q, and the Q changes from 1, so it's actually involving a whole spectrum. But to reduce it to simplicity, it's really all at least omega times the different internal times. So that's why it works. It wouldn't work if this was not the Mother Nature. But of course, it's kind of intuitive. Why not? In other words, your external probe has to match internal clock. We learned that from day one, sort of. I beg you to learn about that through the Maxwell model. Okay, so with all that hard work comes the total simplicity of actually what we found this red curve to look like, this red curve, which is essentially the temperature dependence of your tau. And just for notational purpose, let me try not to deviate. So indeed, of course, it's always so perceived this way. And the way I did it, yeah. So you can think about asking the following question, or expressing it. So we know this is a function of temperature. And we further know that at a different temperature, it will be different. In the book, I call it T0. In your mind, you could even think about this as your reference temperature. And as long as these two temperatures are not the same, this ratio by definition is not 1. Okay. We call this AT in the literature, typically. In fact, if you want to be more careful, you may want to call it AT-T0, so that you know it involves a temperature T and another temperature 0. So empirically, initially, I think it's done empirically, William, Randall, you guys can teach me. I think usually it should be Williams, but I never, I don't check it out. And Ferry. So he's a highly accomplished polymer scientist, mostly working on rheology. And this is later famously just known as author, WLF. This WF is as famous as Coleman's in polymer science. It's very common, commonly appearing in the literature. They found in the 1950s, that one can express this by taking a log of this ratio. When I write a log like this, it's usually 10 base. Did I have 0? Yeah, I have 0. So we'll do some homework with this expression too. But this is the expression. It, if you double check, it satisfies several things. For example, the expression by definition, typically, you should regard it as used for t larger than t0. Okay? In other words, if you know t0's result, you will know your tau at a higher temperature. So what does this mean, looking at this expression? If this is true, okay, this minus sign will be preserved, right? In other words, the right-hand side will be negative, yeah? And that's exactly what it should be, because log of something smaller than 1, because now this one is smaller than 1, because it's higher temperature referenced by a lower temperature, is negative. In other words, 10 raised to a power that's smaller than 1 only if alpha is negative. That's the same reason to say that your log of 10, the 10 base log of something smaller than 1 has to be negative. That's it. So this WF is the celebrated expression here. And it doesn't end here. It doesn't end here in the sense there is a better way to look at it. I have presented in the book, and it turns out I worked out that when we were writing a paper long time ago. But of course, this is a result also in Ferry's book. So Ferry has a book. We call it the Bible, but it mostly just deal with basically elastic properties of polymer. Such a book. But it mostly just deal with linear response. Okay? For nonlinear response, you have to come to this book. So it also indicated in Ferry's book of the following, that the more powerful way to write it, I know the reference temperature is very convenient, T0, but if you choose that reference temperature to be TG, actually, because this reference temperature T0 is up to you to choose, then instead of C, I write it C0, I write it as C. Then the book offers the relationship between C1, C2 versus C0, 2, and T0, and presumably TG. That's offered. That formula is 54A and B. 54 and 56 in the book. There's some advantage about with TG as a reference. It turns out, roughly speaking, the way we do our homework is that C1 and C2 are nearly universal numbers. Why? I hope by that you immediately know what I mean. Meaning, they are numbers almost similar for all different polymers. For example, C1 sort of on the order of 15, and C2 sort of on the order of 40. That fits most of polymers. Don't take me, I'm only giving a small sense of it. Not accurate. But there's whereas if you choose C0, which means T0, then the C10, C20 is going all over the board. Okay. So we'll, for example, do some homework by knowing this. That's it. This gives you a smooth temperature change, just like this red line, quite smooth. And now we can move a little deeper into the question of what it means to reach TG, the glass transition temperature. We have not talked about that. We just just like a caveman, we just acknowledged this red line. That's enough for today's discussion. By acknowledging that, we know that we can invent this temperature superposition idea. Right? Nothing else. We don't even need to know what is glass transition. That's my point. I just want to start from points that are that require minimal knowledge about anything. That's the spirit.